Hello, my name is Herlihy, and I'm a first-year PhD student at EPFL in Switzerland. My co-author is Periklis, and my advisor is Anastasia Ailamaki. So I'm going to talk today about a data processing design that ingests external libraries and optimizes along the operator boundaries in order to expand the functionality of a database system, as well as speed up the libraries in the pipeline that is being ingested. So modern application development deals with increasingly specialized problems that are addressed by specialized solutions. So your average developer is now interfacing with everything from specialized data types, like the stuff that's generated from IoT devices, to specialized algorithms like NLP, OCR, etc. The problem space is getting way bigger, and the traditional database interface, SQL, may no longer be the most natural tool to solve domain-specific problems. So for example, how would you describe video extraction in SQL? So your average developer is not going to be a domain expert in everything, so they will be unlikely to want to rewrite an OCR library in SQL or in a UDF, and they instead will want to reutilize libraries written by domain experts out of the box. So this means, on the flip side, that libraries are often written in the most general or modular way possible, so they can be used in as many contexts as possible. However, if you have a library that works in as many contexts as possible, you lose guarantees about how or on what the library may be run. So you lose optimization opportunities. Library authors often won't know statistics about the data that's passed in at runtime. And when you lose any guarantees about the input to your library, you have to program very defensively. This is good programming: boundary checking, sanity checking, parsing, etc. But if you had stronger guarantees about your data, you could save both time and space. An additional factor is the de facto standard for human readable formats between systems. What you end up with is a flat format like CSV or JSON, which can be very wasteful if the next library in your pipeline just immediately unparses the data. So we end up with a technological landscape where there are very strong boundaries between systems. And this modularity, which is great for development, leads to inefficiency. So I like this quote a lot. You can pause to read it because it shows that this problem is not going to go away. Modular, maintainable, dependable programs are always going to need to be written, and yet we still want to be as efficient as we can. So as a library author, you don't have access to runtime info or heuristics about the data, and neither does the compiler most of the time. So there is a lost opportunity for optimization. So to give you a running example to illustrate the types of optimizations and functionality I'm talking about, I'm going to introduce a pipeline that I call the NOAA pipeline. It is a typical analytical pipeline. You don't need to worry too much about the specifics, but the idea is that it downloads weather data from the National Oceanic and Atmospheric Administration, which is stored in CSV. It then, for each year, calculates which station has the largest single-day weather range. The light blue bubble NOAA decoder is a custom library that processes data to extract relevant values, and range calc groups the input by the first column and does some aggregation for the second column. So to show you how simple it is, this is the pipeline in Bash, but the system I'm discussing today is not specific to Bash. It just accepts analytical pipelines in general. What's interesting about this pipeline is that there are missed optimizations both in sort of typical database form and also in typical pipeline form. So like by pipeline form, I mean in Bash. So task-specific functionality like NOAA decoder that does not have to be developed specifically for the system would not necessarily be out-of-the-box part of a database system. And then there are missed optimizations in pipeline form as well, since there's almost no parallelization or cross-operator optimizations happening. So I'll show you what I mean about cross-operator optimizations. So we have this NOAA decoder as the producer and range calc as the consumer. What it does is it gets some data, does some calculation, and then writes the value to a pipe or any kind of communication channel between two operators. And then on the other side, it reads that data and continues on. So if we peek inside of the operators, we can see a very common pattern of read data, do some stuff with your data. You don't really care what that is. And this is in comparison to an approach like verified lifting, which does require understanding the entire program. In this case, we only care about the edges. You serialize the result of your computation into an output format, in this case CSV, and then you write the result to the output channel. And then on the other side of the pipe, we have a symmetric set of operations. Read data, and the first thing you do is deserialize, and then you do some stuff. So we make the observation that these serialization operators are essentially reversible functions, i.e. we serialize, and then we immediately deserialize on the other side of the channel. And this is wasteful. So it would be better to skip the serialization entirely and write, for example, binary data when the binary formats are compatible. You can combine these operators in a way beyond black box invocation of the libraries themselves. And the goal is to achieve both the extended functionality of these external libraries and the performance optimizations that can be applied into internal database operators can now be applied to external libraries. And in this case, we can see up to a 5 times speedup when we remove this serialization operator in some pipelines. So there are 2 proof of concept optimizations that we are applying to these external libraries in order to get this performance benefit alongside the extended functionality. For parallelization, because libraries are often written to do a single task, they have no information about the operators that precede or follow their invocation. Any built-in parallelism is limited to a single process. When the library is invoked in a pipeline, the person running the pipeline did not write the library, so they may not know the best way to algorithmically parallelize the library. In this chart on the left-hand side, I show the speedup between the baseline pipeline, i.e. the pipeline invoked without any additional operators injected. And then I went in and I manually inspected the pipeline to batch together and parallelize as many operators in a row as I could. On the right side for the serialization, I show the speedup between the baseline, the original pipelines, written by the library authors, and then rewrote the libraries as if they would always expect the next operator to be able to consume their binary data, or even if they are in compatible formats, for example, 2 adjacent Python libraries or 2 adjacent C++ libraries, fuse into one process. So in this presentation, I present GOLAP, which stands for Generalized OLAP. And the idea is that instead of trying to mimic and re-implement the continuously diversifying requirements of data pipelines, GOLAP embraces external utilities and uses them as a means of adopting new functionality. It is based on the observation that the pipeline description itself is a starting point for the database system to learn the required functionality by inspecting and executing the provided pipeline. The core logic is written by domain experts, but the interfaces used to connect and interact with other utilities are often lacking optimization. So how does this work inside of the system? The execution engine starts by accepting libraries and user-provided hints about the behavior. Ideally, you would have library authors register their libraries with the platform ahead of time. This way, instead of the user needing to optimize the library manually, the application developer, who is the expert on how to invoke the applications, can specify how to optimize. These hints or testimonials contain 2 components for now. One is classifying operators based on a relational-like behavior. So for example, if you have a project-like operator, then you can say that it is a transformation function that is essentially stateless. And then you also have traits like, for example, this operator is embarrassingly parallel, or this operator cannot be parallelized at all. In the next phase, we apply pipeline level transformations to the pipeline. So instead of how in a traditional database, the optimization rules know about operators, here the operators know about their own optimization opportunities. So in this case, it is similar to MLIR in that the operators know how to optimize themselves. In this phase, we apply entire pipeline optimizations like, for example, injecting parallelization operators. And then in the last phase, we detect inter-operator inefficiencies, and then we instrument the binaries so that they can be run with instruction level optimizations. So what does that itself look like? We have our state machine for the execution engine. First, you would just run the original pipeline to identify hot paths. Obviously, it's not worth it to optimize on something that isn't run frequently enough. Once you have identified a hot path, you can produce an instrumented binary, similar to how a tracing JIT would do it, and start running that instead of the raw function. Tracing JITs, it's important to note, would not change the data layout itself in between processes. And what this instrumented binary function does is it logs the data itself on either side of the pipeline for each data transformation that it can identify. If data is ever changed, so it's not consistent before and after the pipe, then you know that you cannot get rid of this transformation function. And so you revert back to the baseline. Otherwise, you build a tunable confidence threshold. And then when you are confident enough, you can swap out the binary with an optimized version. So to go back to the NOAA example, what that would look like is we would inject, you would first detect where serialization happens, which is the transformation function I was talking about, and inject logging operators before the serialization on the producer and after the serialization on the consumer. So you compare the raw data before and after, and if it's the same over some threshold, you can apply the optimization. And you can ensure that this project-like classification means that the operator is stateless. And you can ensure that the state does not get in the way by either doing it at an entire pipeline granularity, so you swap out entire executables between pipeline invocations, or you can pre-bake branches in the instrumentation phase so that we minimize any kind of branching so that we can be confident that we are not messing with state elsewhere. So we can see here that our system achieves the same speed up as the manually optimized pipelines that I showed in the earlier, at best case 22 times for a OCR library. And for the single column, double column, we either skip serialization or we fuse them together. And then to see them together, both the serialization and the parallelization operator, we apply it to the NOAA pipeline, which can show us up to 17 times speed up. To conclude, we present a new database design that allows off-the-shelf libraries to be ingested. We use both compile and runtime information to apply both instruction and operator level optimizations that can show up to 22 times speed up. And the takeaway is that we can move the database into an orchestrator role so that we can ingest external pipelines and gain new functionality without paying a penalty. Thank you very much for listening.